First spin.
Welcome to First Spin, a show where I learn how to use the parallax propeller without having any prior programming experience. Rather than do this on my own, I have enlisted the help of Roy and Whisker.
She keeps asking us questions.
I do. And it's
It
a lot
never
of fun.
ends.
Week after week after week after week of all of these technical questions about all of the stuff that lazy programmers like us just skipped over. Addie wants to know all the details, though, which is great for you guys, the listeners, because you can learn right along with her.
Yes. And we can finally get to shutdown procedures.
Oh, yeah, that's
'Cause
right.
you cut me off.
I had to stop you last week.
You shut me down.
Well, we only have a half hour, you know.
You made my reset pin go low.
Oh boy, we've created a monster, Roy.
Yeah, it sounds like it.
She's making microcontroller pin jokes now.
Okay, let's do.
So where'd we leave off? You were doing like startup procedure, and we just like wrapped that up, right?
Yeah, so
Right.
we did boot up procedures, runtime procedures, and now we are going to shutdown procedures, which should go pretty quickly.
All right. And what questions did you have about shutdown procedures?
I actually don't think I have any.
Yeah, it's
I
pretty much
mean-
the same as if you reset.
Yeah, the cogs
you
stop
know.
and IO pins are pretty much floating, right? And let's see, the reset pin goes low. And the only time it comes back up is when voltage level rises above the brownout threshold.
And the reset pin goes high.
Correct.
So it's basically when it's shutting down either by losing power or by you hitting the reset button. That's shut down. It goes into shutdown mode, same thing.
Right.
The application can request a reboot with the reboot command, as it says there, and it will basically act like you press the reset button for a moment, and then it will come back up out of and reboot.
When would you want to request a reboot?
If your program did something to change settings that your code would read at startup, then you might reboot to have the code be reloaded from the EEPROM and start out fresh. That's like one example. There's some other more advanced possibilities there, but primarily it's, you can have a program that's actually larger overall than what's in memory at any given time, and like it loads more of itself in later, and then in order to restart it actually needs to reboot to reload in the original code that it boots up from.
But how does it
So-
remember what it first ran?
Well, when you reboot, it loads up the first 32K of the EEPROM chip into memory and runs that, like we went over last week.
Right.
So if that first 32K then loaded some more of the EEPROM into over top of itself to run new code, or if it loaded something from some other device, then it wouldn't have the original code in RAM anymore. So in order to get it, it would have to read it out of the EEPROM. And a simple way to do that is to just reboot the processor, because it will just go read the EEPROM after rebooting,
Gotcha.
right? And do the startup procedure that
Okay.
we covered last.
Okay. That works.
Mm-hmm.
Well, simple. So, shutdown.
Yeah.
Okay. And now we are on page 20 and 21, and this is the block diagram of the propeller chip. And it's very pretty. But it looks noticeably complex. So I don't know how really to start.
Well, I can
this.
explain a couple things for you.
That would be fabulous.
So as you can see across the 2 pages, there are 8 sections that look basically the same, and they're labeled cogs 0 through cogs 7.
Yep.
And those are the block diagrams of the individual cogs. And then they're all connected with a couple lines there to each other. They go like from one to the next to the next to the next.
Mm-hmm.
And eventually they get over to the end where they're connected from the last cog into the IO pins.
Yep.
And
Yep.
you can see the little mark there that's a little slash with a 32 next to it.
Yep.
That means that there's actually 32 individual lines in that one line, one for each IO pin.
Ah. Wow. Really?
Right.
Wow, that's hardcore.
So, all you listeners out there, if you have the prop tool at this point, that means it came with the manual that these guys are looking at. And what's the page number for this diagram again?
20 and 21.
Okay.
Yep.
You can also just go download the propeller manual from parallax.com.
Correct.
If you wanted to get it, if you're listening to this and don't have the prop tool yet.
Correcto.
So that is the output. Those lines going across the top connecting to all the cogs and then into the IO pins is basically the output of the pins. If the pins are in output mode, it goes out on those wires and goes into each cog. And the little symbols across the top there that look like little wedge, roundy wedge thing with a roundy bottom.
That's the technical term.
Technical term. Those are OR gates, ORing together the output pins of all the cogs together.
Yeah, which we explained last week.
Which is if you have one cog giving an output of one cog giving output of 0, then the OR of that is 1.
Right.
Okay.
And if either of them are on or both of them are on, then it's on. It's a logical OR. It's standard.
And you talk to programmers all the time, Addie, and you may have noticed that sometimes when you ask a programmer a question like, "Would you like a brat or a beer?" and they'll answer yes. That's an OR statement.
That's
if either one of them are true, we answer yes.
Darn programmers.
Or.
Okay, gotcha.
And the other thing that is in those lines coming out, because you can see that there's 2 lines coming out of each cog going into the next one over, and eventually they go out into the other one is the direction register, which is how you tell the IO pins whether they're input or output. So those lines are controlling the pins to say you're in input mode or you're in output mode. And again, those are ORed together. So any cog that has the direction set to output will cause the pin to be an output.
So if 6 cogs or 7 cogs want it to be a 0, okay, it's easier for me to think of this in ones and zeros. A 0, and a single cog wants it to be a 1, then it's a 1?
Yes.
Oh, that's not democratic.
Well, it is just the way that it got designed, and it actually makes a lot of sense when you think about it. Eventually you'll kind of understand that if it were anything other than that, it would be much harder to use the cogs
Sure, I mean,
the shared IO pins, because
sure.
As an example, if it was ANDed together, then the only way that a pin could be an output is if all of the cogs set it to an output.
Oh.
Because AND means that they all have to be true, this and that, right? And do that for all of them.
To continue on with the brats and beer, if I was a teetotaler and didn't want a brat with my beer, and you said, "Do you want brats and beer?" I would have to say no, even if I wanted a brat.
Or a beer.
Man, brats sound good.
What's a teetotaler?
So
somebody who doesn't drink.
Oh, I see. Teetotaler. Right. Okay, go ahead.
So the direction pins and the output pin, or the output control, and the direction control and the output data all go over to the IO pins, and they're ORed together from each cog. So like I said, if any one cog has it set to an output, then it will be an output. And if any one cog has it set high, then it will be high.
Okay.
And again, it's just because if you tried to use something other than ORing them together, you would get some odd results.
Okay.
You know, like I said, you'd have ANDing would require them all to have to work together, and it would be really impractical. And in general, the general usage is like one of the cogs will use a couple of the pins independent from the other cogs. So like one cog might use pins 0 through 4, and then none of the other cogs will use pin 0 through 4. So it won't really have to worry about conflicting. But there are some advanced uses where you might have multiple cogs talking to the same pins, and then that's where the ORing logic matters.
Okay. And I
So-
mean,
Go ahead.
so what happens? Okay, so the hub memory gets loaded. Well, the program, I guess, gets loaded into cog 0, I guess, and it runs the program. And say this program talks to like 4 cogs, and these 4 cogs all want to work with, I don't know, like pin 16, right?
Right.
Like they just
Well, let's back up one step there. So the program doesn't get loaded into the cog initially, it gets loaded into hub memory.
yeah.
And then if it's the spin interpreter is loaded into the first cog, and then it runs the program from hub memory.
Oh, okay.
Clear
Right.
that up because I want to keep you from having that miswording there, because you got to make sure it's very clear you're not running the program directly in the cog in the case of spin. You're running it from hub memory, and the spin interpreter is running in the cog.
Okay, I will eventually understand this. Okay.
So if you then start up your program and it causes multiple cogs, let's say your example, the first 4 cogs to be running spin code that wants to use pin 16,
Mm-hmm.
then depending on how they use pin 16, they may work or they may conflict with each other. If they're all using pin 16 as an input only, then they will all be able to read pin 16 and function, but they will all react at the same time to pin 16 actions because they will all see it change state at the same time. So they won't be independent from each other in that sense. But you could have different code in each cog that if it were reading pin 16, it does something different when, like, say you had a button attached to pin 16 that would cause it to go high when you push the button.
Yeah.
And then all the code in each of the 4 cogs, all the programs that are running on each of those cogs via spin would react to pin 16 going high, and they could all do something different if they wanted to. Or they could do the same thing. But
I have a question then. So Whisker's robotic jib project, right?
Right.
So button on pin 16, right? And you have cog 1 for X axis, cog 2 for Y, cog 3 for Z, each with their own algorithms. And what you do is when you beep, press the button, then all those algorithms go at the same time because they're reading the input from pin 16.
Mm-hmm.
Right. That could definitely be. And then
I see.
In that particular case, the what they're outputting goes to different pins.
Okay.
So like the first cog that's talking to the X-axis is going to output its signals on the pins that you have the X-axis motor controller hooked up to.
I have a question.
And those would be different than the one that you have the Y-axis motor controller hooked up to, and so on.
Okay. I have another question.
Okay.
So say cog 1 sets 16 as an output. Okay?
Okay.
And it puts something out. Can cog 2 read that output and do something as a result?
Yes, in certain circumstances. Like, it depends on if you have something connected to pin 16 that would affect that. But in general, if cog 1, if a pin gets set high, then when you read it from another cog, it will read as high. And
Oh,
that's actually how there's some programs that will do cog communication between each other
yeah.
using the IO pins, and they'll make sure that they're not hooked up to anything that will be a problem.
Gotcha.
Um, and that's somewhat of an advanced feature. Typically,
Okay.
the way you would communicate between the cogs with spin in the simpler way is to just write a value into hub memory somewhere that all the two cogs you want talking to each other agree upon ahead of time is the right location. And
Is there a faster way? Like, is there a preference if we were talking about speed? Like, if I wanted to be ridiculously fast response, would it be
yeah,
better to do intercog communication or hub memory with cog communication?
well, it's going to be able to be faster if you're going between the cogs
Okay.
directly, but it consumes IO pins, and you have a limited number of them. They're kind of precious resource, so you have to make sure that it's really required.
Well,
Like
it's
the
just one
make
though.
well, no, I mean it even one
Is
with
one
one.
more than
Well, the issue is that with only one, you probably wouldn't be able to go faster than writing to hub memory and reading it back.
ah.
What they typically will do is they'll have like 8 pins and they'll do a whole byte at a time,
I see.
or 9 pins because they'll have one that's like a signaling pin,
I
and the
see.
other 8 are data and stuff like that. So in order to make it go faster, because when you write to hub memory and then read it back in another cog, if you coordinate it properly, you can get it going at a reasonably good clip.
Okay.
Um, you know, we're talking, it's still clock cycles away from each other,
Right.
a few dozen maybe clock cycles apart
Which
to
is like
have one.
nothing in the because it's what
Well,
million of
right.
instructions per second.
Well, when we're running at full speed of a standard clock setup for the propeller, you have 80 million clocks per second, and
And about
each,
20 million instructions per second. So
Oh,
well, when you're writing to hub, it's not 20 million because the hub writes are variable from 7 to 22 clocks. Uh,
the 20 is more for
oh, it's 8 to 23
assembly.
actually.
okay,
The 20 million is more for like assembly language stuff, but
right.
I
for
see.
But
spin,
you
it's
could,
obviously slower.
but even in the worst case, if you had the 22 or 23 clocks, uh, wait time to write and then 22 or 23 clocks of wait time for the read, that's still, you know, you still have 80 million clocks. So divide
Mm-hmm.
that by 20, 46, and you can do a lot of them per second.
Okay. Cool. No, that's
Uh,
really really cool.
so continuing on,
Yes.
the other thing you'll see if you go on page 21, if you look at the bottom of the IO pin section, you'll see a little arrow with the /32, meaning there's 32 wires there, and it connects to this line that says pin inputs.
Mm-hmm.
And then if you go across, you'll see that line forks off and connects to each one of the cogs.
Yep.
And then inside the little block diagram for the cog, it ends up connecting to the processor and the 2 counter blocks.
Mm-hmm.
So your input pins come in from this side, and if the pin is set as an input, then when you read the input register, you'll get the values on that pin appropriately. And so all the cogs have all of the inputs. And notice that they're not going through any gates or anything because they don't really need to. They're all just getting the same value on all of them.
Okay.
Because they're inputs, they're not. It's the cog isn't driving them. It's just accessing them and reading them. So
They're not doing anything. They're just acknowledging its value.
right.
Right.
They don't have to drive the line to a value like the output or the direction
Okay.
needs to do. And then in parallel down there where all those where the pin inputs is at the top, you'll see three more.
Oh, 1 second.
Okay, go ahead.
Sorry. I mean, I'm not too concerned about it at this point, but what is counter A and counter B plus PLL?
Okay, so
Roughly.
each cog has two counter circuits built into it, and each of the counter circuits has a PLL associated with it. And there are a number of instructions that we will cover later in spin and both PASM that will allow you to configure these counters to say how often you want them to count their ticks and how many ticks they go before something happens. And the something happens part is related to how the at the top of each of those counters, they also go into an OR gate and then get mixed in with the other IO pins, the
Right.
other output pins eventually up there, so that the counters can actually drive an output pin. So you could set up a counter and cause a pin to be set high and then back low at a regular interval.
So can you give me an example using,
All right, so if you were to hook
I don't know.
a little piezo speaker off of like pin 16,
Uh-huh.
and you turn that counter on to that pin,
Okay.
and you set it to flip back and forth at a frequency that was audible,
Okay.
you would be able to hear a little square wave tone come out of that
Yeah.
speaker. Little
Right.
buzzer. Just to give you a
Wait,
physical
so
world example.
pin 16 sends a signal or
No. So the counter can be configured to drive pin 16.
Oh. So that's
And-
backwards then.
No, it's not backwards. That's forwards. That's what you want. You want there now. There's another part that I'll get to in a minute because that's notice that the input pins also go into the counters, and so you can also count input signals. But let's just finish this output part first. So you can configure the counter circuitry to output a signal, a square wave signal, to a pin, any one of the pins, right?
Oh, okay.
And the counters have many different modes that they can be configured into, and that happens to be one of them, is that it can output a square wave or through runtime manipulation of the counter, you can output pulse width modulation, all through just a simple counter circuit on each cog going to a particular pin. The other side of that is the input pins feed into the counters also, and you can configure the counter to increment a register that is in the cog.
Do you know what increment means, Addie?
Increase or decrease, right?
Increment and decrement.
Yep.
Right.
So change the value of it. I mean, that makes sense because if the counters can both drive and receive, then they can start, say, a counter at 0, right? Or 1 or whatever. That goes through all these little connections here to the pin outputs. The pin talks to the pin input, which goes back to the counter, and then the counter flips to 2, and then 3, and then 4. Something like that?
It doesn't quite work like that. You may be able to configure something like that in some weird modes, but the typical case is you would have some external device hooked up to a pin that was changing the state of the pin to make it go high and low. So in the simplest example, say you had a button that would cause the pin to go high when you pressed it, and when you let go of it, the pin would go low.
Okay.
You could configure the counter circuitry to read that pin, and anytime it goes high, it would add a value to the register, the counter register. And so you could push the button and cause the counter to count up.
Oh.
And
so
or
like
you
one of
could-
those little like tallying things. Little
Exactly.
click things. Okay.
Yeah.
Gotcha.
You know, and that's obviously a very simple example. You could have something else hooked up there that is giving you a signal, and you could count the pulses in that signal. And you can actually configure what it counts. So you can count rising edges or dropping edges. And what that means is you can count when the pin goes from low to high, or when the pin goes from high to low. And that's the point at which it will actually trigger the count to increase.
Okay.
There's other more advanced things that we can get into when we actually get to those spin commands.
Sure.
And have a real example to use with them. But that's just sort of a brief introduction to the counters.
Yep.
There's very long documents that explain all the things you can do with the counters, and it's one of the more interesting and complex pieces of the propeller cog setup is those counters.
Gotcha. Okay.
And they can be used for some really advanced, cool stuff.
Gotcha.
And then just to finish out that rest of that diagram there, I'm sure you noticed where it says video generator.
Yes.
And has some wires going up into those output pins also. So the other really cool thing that a propeller has is that each cog has this video generator circuitry, which can be configured to drive either a VGA connector through just a couple of resistors hooked up to some pins, or NTSC similarly just hooked up to a couple of resistors on a few pins. And NTSC is just like standard video out, like
never the same color.
Never the same color is what it. Yeah, but
is that literally what it stands for?
No.
Oh.
That's just an acronym that is often joked about.
I see.
But anyway.
So those are all things that can be configured to create outputs.
Right. So
Gotcha.
The video generator is typically configured to drive 4 or 8 pins. 4 pins in the case of the NTSC output and 8 pins in the case of VGA output. There are some exceptions to that, but we don't need to go into those. And when you set up the video generator to drive your output video signal, and then you have the appropriate connector plugged into those pins with the appropriate resistors, then you can hook up a monitor or a TV via a interface board or a box and create an image on the screen with a little bit of code in a single cog. And so there's all kinds of drivers available up on the Object Exchange and on the forums for doing all sorts of different resolutions and color and text displays using this video generator circuitry.
Which I'm sure you'll have a lot of questions about once we get to that point, Addie.
Yes.
Exactly.
Yes.
So does the diagram make sense to you now?
Well, we have to finish it up next week, actually.
Right. Still got some stuff left on there?
We sure do. It's
we didn't really get much into the hub memory and the clocks and some of that other stuff.
That's interesting stuff.
Well, we will come back to that next week then. That's all the time we have for this week. Thanks for joining us. You can find this show every Tuesday at firstspin.tv.
Cool.
And that's it for us.
Bye.
Bye.